Engineering 2. Woo. Can you guys let's start with the topic? Surface texture. Let me get some smart water. Don't forget your smart water, okay? You ready? Okay, so you guys probably have seen this before. I usually go and I tell you, hey, put a check mark, and somewhere in the notes it tells you all surface machine surfaces are to be a number and then a check mark, or all four surfaces are to be a number and then a check mark. Or sometimes I probably also give you this note, FAO, and then a check mark. For all cast surfaces, a number and a check mark. So what is that check mark about? That check mark talks about the surface texture and how you control it. Okay. Why do I need to care about the surface texture? Well, I need to care about the surface texture because maybe I want to, I don't know, maybe I want to worry about the appearance, the aesthetics. Maybe I need a certain surface finish such that I don't have a slippery surface. Maybe that concerns is a concern of safety. Maybe I want to create a coating because I'm going to paint. Maybe it's some type of a primer, or maybe just the paint itself. Just go paint it. And I will need to get a little bit rougher surface for the coating to adhere to the surface. Surface preparation, right? Maybe I need to take care of the surface. Maybe the surface that I need is going to require me to have an image light reflection, like a mirror. That might also be a reason why I need to worry about the surface. For me, the one that I have highlighted, and you guys probably will notice here that I made it yellow, is because I believe it is the most important part of the why we need the surface texture. And the reason is because depending on the surface texture, I have something that we call it stress risers. And you guys wondering, okay, Professor Escalona, why do I need stress risers? Why do I need to know about that? Let me try to explain this to you. Okay. Let me see if I got a pencil. Did I bring a pencil? No, let me go get one. Pencil. All right. I'm going to assume that you guys, this is a ruler, right? And if I were to consider the ruler here, I'll make a ruler right there, and I am going to support it at the end. So like this. That's it. And then if I were to try to put a load on top of it, the ruler, were to put a load here, the ruler will try to deflect like this, right? It's all fine and dandy as long as my load is small enough that it doesn't create a permanent deformation. We call that plastic deformation. It's all good unless I have something that we call cyclic loading. Let me adjust the screen here. There we go. Something that we call it a cyclic loading. Where would I see a cyclic loading? If you guys ever were to look at a motor, the motor gets mounted at the bolts. And then this guy rotates. And then somewhere in between the motor, I can also have a shaft. And again, since the motor is rotating, the shaft is going to be rotating. I want you to imagine the shaft that maybe it has a gear. Somewhere in there, it has a gear. And the shaft is rotating. It is transmitting the force to the gear. And the gear, it is most likely will have another gear or maybe a change sprocket. And that will transmit the force somewhere else, like the rotational force, something else. Okay, somewhere else. I want you to imagine this shaft, the one that is in here. And I want you to imagine that it's long. And I mean long. Let's say I'm going to make it, I don't know. Let's make it, let's call it about 10 foot long, right? And again, somewhere in here, I have a coupler. And somewhere in the middle, let's say I have my motor, right? And again, I'm bolting my motor. Somewhere over here, I'm going to have a bearing. Well, it's going to bear the weight of the shaft. And let's put another bearing somewhere over here, right? That it bears the weight of the shaft. So this shaft, remember, it is going to be rotating. As it is rotating, it's going to go for certain revolutions. What is going to be the revolutions? Where it's going to be based on my motor. That's how I buy it. Okay. My shaft, I plug it in to some type of power source, and then my motor will start moving, which is going to cause my shaft to move. Okay. Now, this is what's happening on the shaft as I go and I put this gear. This is my gear, right? It's grasping it and it's twisting it. So your shaft, it is experiencing this. You don't see it because it's really small, right? But it's experiencing a torsion. Considering it, let's call it torsional stresses and shear stresses due to the torsion. Okay? And they are designed to take torsion. So you design all of these shafts because they're going to be carrying, they're going to have gear somewhere in the middle. But they're usually not designed to have bending. What is bending? This is bending, right? Events. This twistiness is torsion. So let's say that my shaft is really long. So it's going to sag like this. Okay. And then also it is going to twist. If I have it really long and it is unsupported, somewhere in the middle, let's call it, remember this guy was about 10 foot, it is going to be sagging. And as it sags, the bottom fiber is going to get a little bit longer. Let's call that guy over here. I can draw it better. The one on the bottom got a little bit longer because it have a tensile stresses within the fiber. And the one on the top, it got a little bit shorter, so it got a little bit compression. As I went through bending, just by the loading itself, before me, I started to twist it. Now, what is the problem with this? I told you the shafts are designed for torsion, are designed for this. They are not designed for bending. When the shaft starts twisting, whatever it used to be, let's say, I'm just going to put the weight itself, or maybe put the chain sprocket, the gear somewhere in the middle, right? Remember, one of these guys, I'm going to put it in the middle. And just by the weight itself, it's going to try to push the shaft down, which is going to create a tension and a compression fiber. So it's doing this, okay? Just by the weight itself. And then eventually I turn on my motor. And my motor, whatever used to be the bottom, as I flip it, now it becomes my top. And as I flip it, my top now becomes my bottom. And it flips bottom, top, top. Well, because it flips, whatever used to be on tension, actually this guy doesn't change. This guy continues having sagging force, right? Which still have tension and compression. But again, whatever used to be the bottom, as it flips 180 degrees, the bottom now becomes the top. And whatever used to be the top, since you flip 180, now the top gets to be the bottom. And if it iterates back and forth. But I want you guys to notice of the stresses. The bottom stress, it was on tension. And when it went and it flipped on the opposite side, then it became in compression. Why? Because I have my ruler that is doing this, and then it flips, and whatever was the top now becomes the bottom, and it flips, and it flips, and it flips, and it flips, and I get something that it is a tension and compression forces. If I were to look at one of these fibers, and if I were to call this guy tension and I were to call this one compression, the top fiber started with compression, and the compression increased as my shaft rotated, and eventually switching from the compression towards the tension. But remember, it flips sides, and it's doing this back and forth, back and forth. This is a cyclic load. Now, what am I telling you this? I'm telling you this because when you go and you have a cyclic load, you need to protect your surfaces. Otherwise, you will have something that we call it stress risers, which can make your material fail much sooner than when you expect it. Cyclic loads just by themselves, it will cause the material to fail in about half the way that you expect the material to fail on. And if you don't take care of your surface, it might do it even sooner. You also want to take care of your surface texture, maybe because you want to have some type of increase on friction. In concept, maybe the surface that you are going to be walking on, it needs to have a certain surface. You also want to take care of your surface when you're doing datums. You guys have seen this before. When I go and I tell you, you have a part and your part needs to be dimensioned. Your part needs to be dimensioned. So now I have told you a dimension from the bottom, But this part is actually going to be, eventually you become a designer, and it's going to get to be manufactured and inspected. And my part actually looks like this. from the top and the bottom. Where do I dimension this distance from? Am I measuring it from here? Or am I measuring it from there? Am I measuring it from there? Most likely, and again, we will talk about GD&T maybe after the exam, but when you are measuring, you are creating a reference frame, an X, Y, and Z plane that I can measure from. Hopefully that makes sense. That's why when I go and tell you guys the bottom. Right now I'm just telling you bottom, but in reality it is more complex than just bottom. I'm just telling you guys, every time that you guys have a reference frame that you're going to start dimensioning from, you need to take care of your surface. And how do you do it? By taking care of the surface. You also want to need it when you want things to mate with each other. And by the way, we're going to start talking about assemblies soon, which is going to require us to understand how things fit. And understanding how things fit is going to require for us to understand the surface of the interfaces or how things fit. Okay, so how do you measure surface? This is really important. How do you measure? You measure it usually with a profilometer. So I'm going to show you my profilometer. This profilometer right here. You usually just go and you turn it on and off. And it usually has two buttons. The one that goes and it switches us from inches to metric, the imperial and the SI system. It also usually has a chart also that allows you to compare between two different ones. What's the difference between this and this? And it also tells you the RA number. It seems to me there is also an RZ number, which I never use. On the bottom, it has a little doohickey that you can, if you want to touch it, it is like a, I don't know, like a stilograph. You can see there is a little dot right there. A little dot right there. And what does it do? All you have to do is you put it on a surface that you want and you press the button, click. And then this profilometer, the stylus on the bottom, it is going to move from the left side to the right side. And as it goes from the left side to the right side, it's going to be displaying a number somewhere here. And you guys are wondering, okay, Professor Escalona, why do I need to know that? Well, let's focus on this. Let's say that my profilometer went from this point to that point. And within that point, I am going to focus on a little portion of it. And it's going to look like this. Okay? And within this little surface, I am going to zoom a little bit more. And it's going to look like this. So let me tell you what the profilometer is doing. The profilometer looks at the tops and it looks at the bottom. Let's call it the peaks and the valleys. The summits and the valleys. And it tries to calculate and actually calculates a mean line. Let's call it a center line. And from that center line, and that's it all internally, you don't have to do anything. It creates a mean. So it creates a center line somewhere in the middle, depending on these tops and bottoms that it finds as it went from one side to the other side. Remember, it has a stylus somewhere at the bottom, right? So it moves from the left to the right. And it creates mathematically a mean or an average. And it reports it to you in the screen. And what do I want the average? So let me read it and then we'll talk about it. Again, the profilometer, it goes and it removes all the waviness, right? Nothing is perfect. It goes from the stylus from one left to the other side. And it finds the center line. And mathematically, it finds the average distance of the surface from the center line. And again, the instrument that we use to measure it is a profilometer, which I show you mine. You can go and buy another one that's going to look something like this. Or maybe you have something much more expensive that is going to look like this one. Again, same concept. The stylus has to move a certain distance. And then since it's going to move a certain distance, it's going to have, as the stylus moves from the left to the right, it's going to have a bunch of waves, like a little earthquake. Within the earthquake, the profilometer is going to zoom in, and it's going to remove the waviness. And as it removes the waviness, it will find the center line, and then from the center line, it will report to you the average. Now, what do I know about this average? Well, the average, what it does. So remember, it goes and it finds the center line, and then it grabs a bunch of wiggly rooms. So if I have a large average, that means that my surface had a bunch of peaks and valleys. Big average. If I were to have a small array number, which is small average, it means my peaks and valleys are small. And what do I want to know about this? I want to know about this because of the surface texture. And it's going to be depending on the different machining operations. What do I do with, how do I produce the part? So, for example, let's say that I want, that I have a shaper. The shaper is this one right here. Oh, I found a shaper. And pretty much what it does, it's kind of like a sewing action. It goes back and forth, back and forth. You can also have a turning. Sometimes they call this center turning. And again, all it does, it is you have your part held like this on the left side, and then you have a tool coming over here and taking away material and reducing the diameter of this guy. As this guy is rotating super fast, my tool is coming in and it's taking away material. That's why we call it turning. You guys will see here, this is the tool. And again, this guy is continually moving left and right, and it's removing the material. So turning is another operation that can give me different surface finish. We also have lapping and buffing. You put a buffing compound, and then you want to same way that you buff your car, right? You can also have grinding. You just have a grinding wheel, and it rotates and it touches the material and it creates a bunch of sparks. So each of these machining operations will have its own surface finish. What can I achieve in terms of surface finish, right? Now, a good estimate to find the RA number, it is grabbing the number that is from from summit to valley, or peak to crest. Let's call it root to crest. It is grabbing that number from top to bottom and divided by 4. Let's say I have distance from the biggest to the smallest of about 1,000. Divide that guy by 4. That will give me an approximate RA number of 250. And again, it's a good estimate assuming that all of these guys are triangles. Depending on the machine operation that you have, you will generate different type of surface finish. Usually when you go and you machine something, it's going to be looking at your tolerance, and it's also going to be looking at your surface texture, because each of the machining operations will produce a different RA number. Shaper, as it acts as a sewing motion, it will get you an RA number 250. If I were to do some type of churning, which is again the one that you grab it and then it rotates and then you go with the tool and take away material, you will notice that my RA number reduces. Why does it reduce? Is because I'm getting a little bit finer, right? I went from, most likely I would have like a rough turning and a semi-finished turning and then a finishing turning. So reducing the turning passes. What's the difference between a roughing turning, semi-finished turning? Is you take more material in the roughing, and then as you're getting finishing, or you're about to finish the part, you will have a finishing turning, finishing moves, let's call it. So a lot of, you take away less material. So to increase the surface, but make the surface finish better, right? You can also have grinding, right? And remember, grinding, you take away not chips of material. You take away sparks. And taking away sparks is going to increase, it's going to fine-tune your surface texture, which is going to reduce the RA number. Remember, the RA number, it is the average. So if I were to have a 25 and then I divide it by 4, I will get about an RA number of 6. An RA number of 6. Lapping, and on the other hand, remember, it's a secondary operation that will be more buffing and lapping. You will have your buffing compounds and you will like that. So you guys will notice your peak to peak will be 20. If I want to have peak to peak, let's call it from top to the bottom, and divide that by 4, you will get about RA number of about 5. So the smallest the RA number, the smallest the average. The smallest the average, the more fine-tuning the part. That means going from turning, let's call it going from shaping, or going from turning to finish grinding, and then going to a next operation, which will be lapping or buffing, right? So how do I call this out? This RA number, all it is an average of the surface. And you go and you report it in your check mark. If I ever notice, hey, Professor Escalona, what is the number that is right there? Oh, that is that's the average number. That again, we got it from the profilometer. And that number goes in the check mark. You can have the metric system, or you can have the imperial system. For the metric system, you measure in meters, and you report it in micrometers, or 1 times 10 to the negative 6 meters. And you can also report it in micro inches, or 1 times 10 to the negative 6 inches. Now, which one is better? Which one is higher? Which one is smaller? So let's think about it, right? This here, from here to there, this is about 1 inch. Okay, a meter is papas, right? So a meter, I'm not even going to draw it because it doesn't fit in my paper. 1 meter is actually hell big, right? So if I go and I tell you you have 63 micrometers, or I have 63 micro inches, you guys get the thing, right? You guys try to understand what's going on in terms of bigness. One's reported in meters, one's reported in inches. That's why you guys will notice some numbers are going to be higher, some numbers are going to be lower. And why these numbers are going to be is because in in 1 meter there is about 40 inches per second. Somewhere about here, right? It's a good estimate. So if you guys want to know, okay, so what is the equivalent of meters to inches? It is dividing it by 40. Grabbing whatever you did in micrometers divided by 40 will give you what you do in micro inches. For example, oh, by the way, before I do that, why do we only put a check mark? You guys will notice here on the bottom, there are other things going on. There is a circle, there is a number on the left side, one that looks like a triangle, and the only one that we usually do is only the first one. Use a check mark. And let me read it why. The basic symbol, roughness average specified, is the one that we usually do. And why? It is where the roughness height is only indicated. The surface may be produced by any method. Why do I only want to do that? Well, because we're not machinists. Let's call this guy means and methods. You tell it how you want it, and the people that build it, we don't care how they do it, they just need to get it to that size, right? Now, the other ones, you guys will notice that it gives you a little bit more telling them what to do, where the material removal by machining is required. Now you're telling them how to do it. Maybe they don't have to machine it. Maybe just will get a file and we'll give it the surface finish, right? So, what do? We do the first one because we are not trying to dictate how the machines do the work. Let's look at a couple of them, right? For example, let's get this 250 micro inches, and we're gonna divide it by 40. 150 divide that by 40, and I get about 6.3. Why? Because I told you guys in 1 meter there is 40 inches. That's why. So if you guys want to know the equivalent, maybe you forgot one and you want to do the other one. That's how you do it. Just divide it by 40, you will get the other one. Now I want you guys to notice one thing though. As I previously told you, you need to take care of your surface. Because if you take care of your surface, you'll be able to develop all the strength of your material, especially when you are dealing with moving parts. Because when you're dealing with moving parts, your part might do this as it rotates. It might create a cyclic loads. So anything that is going to be static, is not going to move, or is going to require things that have a lot of wiggle room, it can be used with a large RA number, a large roughness. But as I'm getting things that are moving, I need to decrease my average. And I need to fine tune my surface. The bigger number is the bigger average, bigger discrepancies between the peak to peak. So it is going to be the rough type of parts. 250 micro inches, where the clearance surfaces are rough machine parts. 125. Mating surfaces static, they don't move. The clutch disc faces surfaces for soft gaskets, something that requires the roughness. 63. Piston pin boards, brake drums, cylinder block, top gear locating faces, gear shafts and boards, ratchets and pole teeth, mill thread, rolling surfaces, gearbox faces, piston crowns, turbine blade. So as you guys will notice, when you go from here, from just rough and static, as I'm going lower and lower, I'm getting into things that are going to start to move. bearings, gear teeth, motor shafts, engine cylinders, jet engine blades, ball bearing, I don't know what it says there, ball bearing something, hydraulic piston rods, gauge faces, things that you're gonna use to inspect other surfaces, bearing balls, gauges or mirror like or micrometer anvils. Anvils is again for inspection purposes. So the smaller the RA number, the better the surface finish. The bigger the number is because most likely I'm not going to have machines that are going to be moving that are going to experience cyclic loading. The smaller the RA number, the more secondary operations I will require to achieve that. I need to take away my bazooka to be able to get to 1 micro inch, which is going to require more money. But again, you'll use it only for special applications. So when you are looking at what RA number to use, you will use it depending on the function that you require. Every machine in operation will have a range of what it could produce the part at. Okay? For example, let's see if I can show you this. And if you want to look at this, this is an RA comparator. Let me turn on the light. This is an RA comparator, and if you guys want to look on the left side, that tells you latch, buffing, and lapping. So this one, right? Mirror looking like. Just will notice you have 2L, 4L, 8L. So the mirror looking like, I would pretty much buff it and grind it. Right? Before I can get it to the lapping, which is the buffing, I will have to go through the milling process, roughing, semi-roughing, finish. I mean, all of these are called either milling or the lathe, right? We call that turning if it's on the lathe. Then maybe say we started with rough turning, semi-finish turning, right? So you started with a big one like this, right? You grab it, like if you want to have a drill, like that, you grab the material, then you come with a tool, right? And you take away material. The first one, you take a bunch of material, as much as possible. That's the rough turning. In the second one, you go back and you take away a little bit less material. Let's call it semi-finish turning. And then you go back again, finish and turning. So now it has the right size. Oh shoot, I need to decrease my tolerance because I have a special application. I need to go get myself a grinder. So now you will have a grinding tool, right? A grinding wheel. And the grinding wheel will go and create chips, not chips, sparks. Okay? And then you go and you say, now that I have my sparks and it's all nice and there, let's go and lap it. Let's take care of the surface finish. So as you guys will know, in here you have 250. Let me see if I can show you. You got, let's see, this guy is about a 500 ST, which stands for shape turning, right? Like a sewing motion, right? And this is shape turning. And then you also have 500P, which it has for profiling. Profiling is kind of like a milling, it goes around. So what do I mean with that? So sometimes you can also grab the piece of material and you squeeze it on a vise. Let me see if I can draw a vise. My vise will look like this, right? And somewhere here I will have a parallel that will hold this part on the top, right? And then I will have the tool on the top, right? Look on the top, and it goes around the part and it takes away material, right? That is profiling. So you guys will notice you have the P for profile, it's a little bit better. And then you also have the M, and it seems to me the M is for the milling. Milling is when you go and you grab the same tool and then you go and take away material like this, right? You can go like that, right? Take away material as you move the tool and it cut into the material. So you guys will notice there is a series. You can have the same 500 surface texture if you want to look at it in the profilometer, right? You go over here and then you click on it and then put a number. Click on the button and it will give you a RE number. But each of them will give you the average will be the same, but you guys will notice each of them is a little bit different. And as you are going from, let's call it milling and turning, you can also have milling and turning for a much lower RA number, 125. You can achieve it. You have a range of it. There's a range that you can achieve depending on what you are required to do. However, as you're getting closer into the numbers that are a little bit smaller, here I got 32, right? You will be able to only do it with certain operations. For example, for the SD, I can do shape churning, I can have lapping, I can have the jig, which is grinding, I can have the G for grinding, more grinding. From 16 and below, you will only be able to achieve 16 and below with grinding and with lapping, which again is the one that you kind of buff it, right? So just be aware that in order to be able to achieve this type of surface finish, it is going to require a certain machining operation. And certain machines can only achieve certain RA number. If I don't have the tooling and you are calling out a crazy RA number, crazy, I'm talking about small RA number. Remember, there are micro inches and micrometers. That's called microns. You will notice that the application, you can only get it with certain amount of tooling, certain amount of process. And sometimes you got to go to several processes to be able to achieve it. Now, you guys want to have a better description of it. I give you guys the micro inches and the micrometers. Remember, the bigger number, the rougher the material is. We are not going to do anything in the 1000 or the 500. There are things that are rough. We're going to do from the 250 maybe all the way to the 32. 250 coarse production surfaces for an important clearance and cleanup operations. 125. It is the roughest surface recommended for parts subject to load, vibrations, and high stresses. It is also permitted for bearing surfaces where motion is slow and load light and infrequent, or in medium commercial machine finishing. So you guys will notice every time that I go and I put my drawings, most likely I will tell you FAO 125. FAO stands for, remember, your notes always usually say, unless otherwise specified, and then it has a bunch of notes. And I usually give you this 125 because it's a medium commercial machine finish. That means you literally can achieve it with any type of churning or milling operation. And I will give you into the middle. Let's say I'm not grabbing anything that is going to be let's call it have high motion, high speeds. Anything, everywhere else, finish all over 125. Anything that I have to actually decrease it is my RA number, then I will give it to you smaller than 125. For example, here I got the 63 for good machine, right? It is MIB specified for closed fits and used for all stress parts except for fast rotating shaft and axles. So I still do not use 63 for moving parts, but I am using good machining. So my surfaces will be a little bit better. So I went from 125, right? Which this 125 I can achieve it with pretty much any milling operation or any turning operation. And I grab into the 63s. The 63s, again, I'm still not going to use it for finishing up, for moving high rotating parts. Right, so I'm going to skip this one. If I want an ice finish with a rotating part, will be this one. And if I want to start doing rotating parts, I need to jump into the 30 seconds, into the 32 micro inches or microns, which is this area right here, right? Much finisher. So I went from this rougher to this guy a little bit better, right? And as I continue going down, right? Again, the 32, that one you will be able to see that you have actually, let's see, produced for lathe shapes, milling machines, etc., but relatively easy to produce by center, less cylindrical and surface grinders. So for this point of time now, I need grinders. Also, extruding, rolling, and die casting may produce a comparable surface when rigidly controlled. It is used for bearing when motion is not continuous and loads are light. When finer finishes are specified, production costs rise rapidly. After this point of time, anything below 32, prices are going to skyrocket. Because remember, that's the point when I was doing grinding, the previous one. This guy had to actually have fine cylindrical grinding. Anything below 16, honing, lapping, or buffing. I went from the milling or turning into grinding, into fine grinding, into honing and lapping, that's buffing, right? Number 4, costly refined surface produced by honing, lapping, and buffing. It is specified only when the requirements of design make it mandatory. It is required in instrument work, gauge work, where packing and rings may be slide across directional surface grain. When I have special applications, anything that is below only the finest modern honing and lapping, buffing, and superfinishing equipment will be able to achieve the RA number. So the bigger the number, the rougher the material is. Anything that goes between 16 and below, I will have to have high quality grinding. And it gets to a point at which I cannot achieve it with grinding, especially 8 and below. I can only achieve it by buffing, lapping, and honing, which is all buffing operations. So, as you guys will imagine, I want to hope that you will imagine that just the same way that tolerance happened before, as I decrease my tolerance, the cost increased rapidly. If I were to mess with my surface texture or my surface roughness, the cost will increase rapidly, right? So, for example, I can have 125, which will be this one, the regular that I usually use, 125. Let me see, move my camera out of the way. I can start with this 125, which is the regular that I usually use, and move it to let's do it to this mirror-like finish, which is about a 2. How much did I increase in price? So 125, I'm right here, and then I went to about a 4 and a 2, right? You guys would imagine how much costly this is, right? This is the increase in times, right? So I went from starting from 500, which will be whatever price it is. If I went to 125, I increased the price 3 times. And if I went all the way to the roughness of 2 micro inches, I increased the cost about 10 times, right? So you guys would imagine the more operations that you do, the longer it's going to take you. The bazookas you're going to have to achieve to be able to get to the surface texture, which increasingly is going to put a dent in your pocket. It is important for things that are going to go under cyclic loads to take care of your surface, because if it's already a cyclic load, any type of stress concentration, roughness, surface condition will automatically decrease your strength of the material already. So just by going on the cyclic loads, without even worrying about the surface finish, just by having a stress that are cyclic, your strength is going to decrease by about half. Whatever I started with my material properties, I got to chop bit. So I can only get half of the strength. And if I don't take care of the surface finish, I can decrease even more. Let's say that I don't do anything with the surface, and I cast the material. Cast is, melt the material, put it in a die. I can decrease my strength. Let's see how many the strength I start. But here is the ultimate tensile strength. Let's say that if I want to have something that has a high strength, I can reduce it from 20% to 70%, right? Just because I didn't do anything with the material, I just put it the way it was. If I churn it, I can reduce this. I will reduce the strength. If I do, let's call it fine churning or rough churning, I decrease the strength between 10 to 30%. If I grind it, I decrease the strength. Remember, grinding is just sparks, right? If I grind it, I decrease the strength about 8%. So I need to polish it. In fact, I need to fine polish it to not reduce it anymore, because I started with full capacity. I go under cyclic loads. I reduce my strength by half. And if I don't take care of it, from that half that I have, I take even more. That's to the point that your strength is gone. That's why every time that you have things that are moving, you go and you take care of it. In fact, usually don't want to spend too much in machine operation, so you buy the shaft. You buy it as a TGP shaft. Churn, ground, and polish. What would that do? I would ensure that my parts that are going under cyclic stresses, cyclic stress tension and compression, it will not decrease its strength that it's already been decreased because it's going under cyclic stresses. Anything that is moving, take care of your surface. And I think that's what I'm going to leave it. Next time, we'll most likely finish it in the lecture. And then most likely also we'll talk about your assignment. So let me stop the share. And let me pause my video. Good morning, engineering 2. Can you guys hear me? Yes, thank you, Eric. All right, let's start the class by sharing my screen, and then we can talk about what we're going to do today. Let's start. Back from where we were last time. So if you guys remember, last time we met, I told you that there are many reasons why we apply surface texture on a part. Different surfaces might have different surface textures. That might be used for aesthetics, maybe be used for safety. There might be used for, I don't know, for to be used as a data. There are many ways that you can use, but I think the most important one is, especially when you have things that are moving, do you want to ensure that the capacity of the material gets conserved, gets to be retained. If I were not to take care of the surface texture, I might reduce the strength of the material and will fail at much lower stresses than intended. We also talked to you guys about what surface texture is. All it is, I have a little profilometer that it goes with the stylus, it goes a certain distance, it take away the waviness, it finds the midline or the center line, and then it takes the average, and that's what is reported to us. The RA number is reported in the 10 to the negative 6, or as a micro inch, or as a micrometer. Remember, it is measured by the profilometer. We also talk about different type of machine operations that will give you a different range of surface texture. If you decrease the RA number, that means you're decreasing the average, which means you're making the material more expensive, as I will have to go through more operations. So make sure that you go and you apply it only when you need it. If for whatever reason you have a shaft that is moving, sometimes you just would buy the shaft. And you will buy it as what we call it TGP. TGP. Churn, ground, and polish. And it will be churned, it will be used with the lathe, then they're going to grind it, and then they're going to polish it, ensure that it has a nice surface texture, such that you can use it for moving assemblies. And I believe also, we also talk about the cost. Again, same concept. If you do more operations, it's going to cost you more. And then we also said we usually only do the check mark, or at least in my class, we're only going to do the check mark, because we're going to tell the machinist you can do it however you want. Just make sure that you get the surface finish number, which is my RA number, my average roughness number. If you were to draw this by hand, this will be the dimension that you will use. So you will, again, you're only doing the check mark, right? And this X stands for the text. So usually the text on engineering is either going to be 0.1 or 0.125. In our case, it's going to be 0.125, right? That means the distance from here to there, if this guy is 1/8, right? That means the distance from here to here will be 3/8, and the distance from here to there will be half of 3/8, right? Because half of 3 is 1.5, half of 3/8 will be 3/16, right? And again, you have an angle that is 60 degrees, so 60 degrees here, 60 degrees there, and that's how you draw it, right? If you were to draw it, we are not going to draw it, so you guys know. I'm just going to know. Let me see what else do I got here. We talk about cyclic loading. We're talking about this applications. I remember I told you usually we only do the RA number, but there are more, let's say, more specifications that you can do, right? You can tell it the roughness width. It seems to me you can tell it roughness width cutoff, the waviness width, the waviness height. You can even tell it what's going on in terms of surface. Because you guys remember, I showed you guys my little cookie, which I don't even know where I left it. It's going to look different depending on different operations. Now, if you want to give them specifically the shape of your waves, right, then you can go this way. And again, I'm going to assume that this type of callouts are when you're actually doing, I don't know, something like super precise that it has to be a certain way. In the drawing, how do you call it out? Okay, you've seen this before. All machine surfaces are to be a number and your check mark. Okay, and it's pretty much it's telling you every time that you go and you put it on a machine and you start doing machining operations on it, the surface that is going to be there is going to be based on this average number. The surface, as I put it on the profilometer, it should be in micro inches or micrometers. Okay. You also have the cast surfaces. What is the cast surfaces? There are two types of castings. We got something that we call it die casting, and we got something that we call it sand casting. And what's the difference with the casting? What they do is they grab the material in the liquid state, they smelt it out of the ore, they get it to the pure state, and then they put a couple of alloys. And one of those alloys is going to be silicon, especially when you're casting things. And the reason why you add silicon, and you usually use a high content in silicon, I would say maybe like 5 to 10% of silicon, 5 to 10% of silicon. What it does, it increases the latent heat of crystallization. It makes the combination of your alloy, it makes it harder to cool off. It requires more energy for it to cool off. And what would that do? Well, you get it in the liquid state, and then you put it in a die. So if I were to make it a die casting, it will have literally just top and bottom pieces of metal, and inside of it, it will have a cavity, right? Which, let's say that's the shape that you want, right? This is my part that I want to get out of it. And when I go and I put the liquid into an opening, put it here, it will be able to go through the cavities and eventually fill up my part, let it cool off. I will open the cup and the drag. That's how you call it. They're actually called flask, or sometimes this guy they call it cup, and then you call this guy drag. They pretty much just go put the metal, it solidifies, it opens up, and then you have a part that looks like this. This is die casting. Now, if you were to do sand casting, it will be the same concept. The only difference is you're not going to have a machine. This is material, this is metal, right? Which is most likely going to have a higher melting point than whatever you're pouring in, right? Because it's other molten metal. Maybe this one is, I don't know, a really high alloy steel, which is not going to solidify when you put other metal there, right? It's not going to become liquid. It's going to have a really high melting temperature, more than whatever I'm pouring. The sand casting, you do the same. The only difference is that you put sand and you mold it with the sand. Usually you have like I don't know, something that has two pieces. And again, if you guys ever take materials, we will do this in the lab, so we'll give you a better sense of what it is. Once you do this type of operation, you can also have a surface finish. Usually the RA number is going to be much higher because you are doing it through casting, not through a machine operation. Remember, the number indicates how rough the material is. The bigger the number, the rougher the material is. The smaller the number, the finer surface you have. You might also have a note that says FAO, and FAO stands for finish all over. That means you're going to do pretty much machining everywhere, right? All over the place. And since you're going to be machining everywhere, you want to ensure that all over the part, no matter where you see it, it will have a minimum requirement in terms of the surface finish. Again, that's why AO stands finish all over. Now, how do you apply it? How do you show it in the drawings? Okay, I want to tell you how do I, let's call it Escalona standard of engineering. Okay, I'm kind of like PPT or how I point things out, and then I want to tell you what I like and what I don't like. Okay, so let's see if I can put this guy next to it, and I can tell you what I like and what I don't like. Let me see if I can get another piece of paper. And since you guys will you can consider me as your employee, since I am the one that's grading your drawings. Let's say, how would I do it if I want to have this part? Okay, so here I got a breakout, and here I have a part that looks like this. And it seems to me they want to have a surface finish here. So this one, perfect. I love it. Nice. You have an extension line, and then you have an arrow, and then you have a check mark. Beautiful. Perfect. No questions about it. The next one. It looks like this, then it looks like this, then it looks like this, and then it looks like this. Okay. This guy went and they created an arrow like this to account for the surface texture. And then I went over here and I made another arrow somewhere over there. That's also okay. I think I don't like these arrows going sideways, but it's okay. Normal operation. Let's continue to the next one. The other one, it seems to me that looks like this. And then it has an extension line. And if you guys recall correctly, I told you there is an invisible boundary that I'm not supposed to be there. So if I were to have this condition, I usually would want to get out of the part, right? I don't want things too close to the part. So in my case, maybe what I will do, I will do something like this. Right? That way I will be away from the part. And the one that I really, really don't like, this one's okay, I guess too, right? But this guy, I don't like it. No. Why I don't like it? Because you're on the part, right? It's kind of violate or already existing rule. And there is the whole thing is to try to make it nice as clear as possible. So I don't like it. Don't use this method. Do not put surface finish right on the part. You can also, if you were to have a whole callout, you can put the surface finish right next to the dimension, or you can also put it in the shoulder. Right? And don't forget, you can also put it in the notes, right? Okay, let me see what it says. The surface texture on specific surfaces is specified by placing the texture symbol directly on the surface. I don't, like I said, not directly on the surface. I don't want you to do that. On the tail of the leader pointing to the surface, or an extension line extending from the surface for cylindrical features. The symbol can be on the tail of the dimension leader or next to the dimension number. Again, this is the tail of the dimension leader or right next to the dimension number, right? Again, all of them are fine, I guess. This is the only one that I don't like. And the only reason why I don't like it is because, again, it violates the other rule that we have. And we don't want to have completing. Some of them, yeah, some of them, not. No. Just make it clear, move away from the part. Okay, now, this is the most important slide of the whole lecture. And remember, I don't like this. I don't flip the surface finish and say, I'm going to just put it backwards. The symbol looks like this. Oh, I'm going to put it like that. No, don't do that. Okay. Second, don't go and don't put things inside of the part. So move to the side and then put 125, right? So away from the part. Same concept with this one, right? You can also put, a extension line for 125, or you can also put a leader, which I not prefer on the leader. I don't think it looks better. I think the extension line looks much better. 125, right? Do not put things right next to the part. Now, the most important note, let's read it and then we'll understand. Finish marks must be repeated in every view whatever surface appears as an edge, even as hidden surfaces. Let's imagine something. Hopefully it makes sense if I explain it differently. So let's say that I have a part that looks like this. Right? So it goes and it has a hole, okay? And then the hole is on the top view. So if I were to say, you know what, I want to ensure that when my hole gets to manufacture, and the whole surface will have to have, I don't know, 16 micro inches, whatever that's the case, right? 32, 62, whatever that's the number I gave you. So if I were to do the front view, it will look like this. And again, I'm trying to do as quick as possible so I can finish the lecture. And then if I were to look at the top view, it will look like this. And then if I were to look at the side view, it will look like this. And then I told you, you get to place it in the surface everywhere, pretty much every time where I see it as an edge. Now, can I see the surface of the hole as an edge here? Yes. Okay, surface of the edge, right? Can I see it here as an edge? Well, yes, you can see it. There's a hidden line right there. It's a hidden line. It's an edge. I can see it as an edge. Can you see it on this one? Yes. I can see it as an edge. And this I see it as an edge. I have to call it where I can see it as an edge. So how will you call it on this one? Well, you will come over here, put a center mark, boom, go with the arrow. Then you will have a diameter, blah, 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 right? Whatever that's the case. And at this point of time, I can go and I can put it right there. That's one way of doing it. Or I can put it right here. Boom. Now, I'm done with this guy. I need to go to the other views that I also see it as an edge. And I need to call them out. For example, here, I'm going to come over here. And then I'm going to put an arrow 60 micro inches. Here's the same surface, it's just a different edge. I'm going to go somewhere here and do the same concept, 16 micro inches. Now, in Inventor, you guys have done those symbols before, but I don't think, let me see if I can open it better super quick. You guys have an assignment, which is, I believe this one, right? And it is asking you, the surface requirements are FAO 125. So what do you think the FAO is going to be? It is finished all over. Means you're going to put it in your notes, which is going to say 102 FAO 125. See, that's going to be your note. Unless otherwise specified, because it's telling you the except. And then if you were to look to the first note, it says the three surfaces that make up the inside of the slot are 16 micro inches. So literally these three surfaces. If I were to look at this, the three surfaces that make up the bottom, which are, see if I can do high, these ones, right? Where would I see it as an edge? Well, I will see it, oops, sorry. Let me see if I can highlight something in the middle. So I will see this guy as an edge, right? So I gotta call it out because I see it as an edge. Let's go to the other views. Where else would I see the three sources from here. Well, the edge that I see here is that one, and that one. Right? So they're also the edge. Remember, it's the bottom surfaces. And then if I were to look at the top, let me see, look at the top. If I were to the top, I will have that one, that one, that one, and that one. And again, it is because depending on how I look at it, I will see the sides of it. Like see these guys here, that one, and that one is the edge, or is the surface that I'm trying to do, and you will see them as edges. You see, that's the edge, that's the edge. So now, when you call them out, you gotta show them in the drawing every time that you see an edge. So for example, in here, you will notice that I put an extension line and boom, call it up. And then that will cover this surface. You also need to cover, I don't know why this one is not called out. It should be called out somewhere. Yeah, that's not good because I think I told you, did I tell you the 4 or the 3? Let me read the question again. Some may think that might have a mistake. Let me see what it says. The 3 surfaces that make up the inside of the slots. 1, oh, so it's the inside, guys. It's not all of it. It's just the inside of the slot. So just that one. That's it. Make sure you read the thing, otherwise you'll make a mistake like me. Okay, so it's these 3. That one and that one. Okay. So since I see it here, I will call it up there, and then I will call it with arrows from the other side. Okay. And I could also easily went over here and come over here and went to the 16, and then come over here to another extension line and go 16 here. That could also work. Less arrows, less going into closer to the part. And remember, I'm doing the green one, right? I don't see actually this one as an edge, since I found out that it's only the top one. So you will see this guy, and that's why you will see it there, right? And if you were to go to the top, well, it will be this line, that line, that line, and that line. Why? Because I see him as an edge. Hopefully that makes sense. You guys will notice also in your assignment, it's telling you where you have a rimmer, when you have a ring hole, you also need to add surface finish. In fact, if I were to look at the instructions, it tells you that you're supposed to apply 32 microinches. So this hole needs to have 32 microinches. So again, where would I see it? It is this hole, right? Which means it's this hole, which means the hole, right? So I come over here, boom, surface texture. I come over here, and it is called right there, okay? And then you come over here, and in this case, I think I removed the hidden lines because it was too crowded with all the hidden lines. So in this case, I don't see it as an edge, and that's why I don't call it out, because I can't see the edge. Now, when are you going to put hidden lines or not? I'm going to tell you, for whatever reasons, they don't supply anything in terms of design intent, and it's way too crowded to actually see anything. I will most likely will tell you, hey, remove the hidden lines from this view, and make sure that you understand how to do that before your exam. The rest of it should be pretty straightforward. It seems to me here I'm telling you also that this hole is supposed to be 32 microinches, and since you see it here as an edge, then you also call it out 32. Boom, done. And this pretty much wraps up the surface texture. I give you this in your lecture. It should be in your Dropbox, in your lecture folder. And again, I will give you an idea of what which of them do, each of the 25, 12.5, 6.3, what each of them do, and what kind of process can be achieved in terms of RA number. Okay. In Inventor, let's see if I have something that I can open. I can tell you how you do it. Let me change the project. I think I have a different project here. Command computer. It's common. Just way too many things going on. You need to say done. And let me open this in class that I have here. Okay, so command computer, get to it. And I don't have anything. No, beautiful, huh? Let me see if I have something that I save. I usually don't save my work because I oh, there we go. They won't have something because I don't need it, right? I don't need to save anything, or I don't have to submit any homework, right? If you guys go to the Annotate tab, there is a portion where it says surface. All you have to do is come over here wherever you want to place the surface, Boom, place it. And I would suggest do not only click once and then right click and then you continue. So we'll place it right there. And will allow you now to put your number on, let's say 32. Boom. And remember, all your text should be horizontal, so this is wrong. So by that point of time, you can do a couple of things. You can grab that dot and you can move it to the side, right? Anywhere here. And if you want to go and you want to make a leader, you push it to the side and then you lift it up. Boom, done. That's how you make it surface finish. If you want to put it on the hole, you come over here and then you double click super quick. Boom, boom. And then usually when retain the last number, you say, okay. And if you want to put it on the shoulder, you just got to go close to the shoulder, click on it once, right click, and continue. And if it tries to flip it, remember that dot, you'll be able to move it, put it in the right place. Done. That's how you do surface finish. I would suggest again, try to start and then just click on it once, wherever you want to place it, right click and continue. Place the number that you need and say okay. And then if you want to move it, all you have to do is select the dot and then drag it and put it wherever you want to put it. You can also put arrows like this. You can come over here like that. And if you want to add a leader, you can just right click and there should be add a leader, which allows you to select something like that. And if you want to remove a leader, you can just click on delete the leader, select what you're going to get rid of. Boom, done. Simple. Surface finish. That's how you apply the surface finish. Remember, to apply the surface finish, everywhere that you see the surface has an edge. Has to be an edge, okay? And that wraps up surface finish.